Pick up your hand. Look at it. Go ahead. Really look at it. That's roughly 10 circumflex. 28 atoms right there. Octillion scale particles, if you want to put a name to it. And I want to tell you something about those atoms that's going to sound wrong when you first hear it. And then it's going to sound obvious. And then it's going to stop sounding obvious again, once you think about it a little harder. Those atoms are not what's holding your hand together. Now, I know what you're thinking. You've heard the atom story. Nucleus in the middle, protons and neutrons packed in tight, electrons buzzing around the outside. The electrons form a cloud, and when two atoms get close to each other, those clouds push back. And that's why solid things are solid, and why you don't fall through the floor, and why your hand is a hand rather than a collection of particles drifting apart through space. You've got that picture. And that picture is, I want to be precise here, not wrong exactly. But it's not the picture. It's a sketch of the picture, missing the thing that actually matters. Here's what I mean. When you press your hand against a table, something pushes back. You feel it. The question is, what? And if you say the electrons repel each other, you've given me a name for the thing, but you haven't told me the mechanism. How do they repel each other? Two electrons on opposite sides of your hand, separated by centimeters. How does one know the other is there? This is where it gets interesting. Because the answer isn't matter. The answer is fields. Let me explain what I mean by a field, because people use that word and then wave their hands and hope you don't ask follow-up questions. A field is a physical quantity that has a value at every point in space. Temperature is a field. Every point in this room has a temperature. But electromagnetic fields are different in a crucial way. They're not just descriptions of what matter is doing. They're real physical things, and they carry energy, and they can exist completely independently of any matter at all. Maxwell figured this out in 1865. What he did was take four equations, Faraday's law, Ampere's law, Gauss's law for electricity and magnetism, and he looked at them together, and he noticed something. Changing electric fields produce magnetic fields. Changing magnetic fields produce electric fields. If you get one going, it produces the other, which produces the first one again, and the whole thing propagates through space on its own. He calculated the speed 3 × 10 circumflex, 8 meters per second. That's the speed of light. This was the moment Maxwell understood, and it's a genuinely staggering moment, that light is an electromagnetic field propagating through space, not something traveling through an electromagnetic medium. The electromagnetic field oscillating is the light. Now here's why this matters for your hand. Your hand is largely empty space. You've heard this. The nucleus of an atom is roughly 10 circumflex 15 meters across. The atom itself is roughly 10 circumflex 10 meters across. That's a factor of 100,000. Imagine the nucleus is a marble sitting in the middle of a football stadium. The electrons are somewhere up in the stands, maybe, if they even have definite positions, which is a whole other conversation, and everything between the marble and the stands is empty. If you could compress all the actual matter in your hand into a sphere where nothing was wasted, where the nuclei were touching, you'd end up with something about the size of a human cell. Maybe smaller. The rest of your hand, almost all of it, is not matter. It's field. And it's the electromagnetic field that makes your hand feel solid. When the electron clouds of your hand atoms get close to the electron clouds of the table atoms, the fields interact. The electromagnetic force carried by photons, which are the quanta of the electromagnetic field, pushes back. You feel that as solidity, as pressure, as the table supporting your weight. What you're actually sensing is field interacting with field. So when you sit down in a chair, you're not really sitting on matter. You're floating. And this is the honest description. You're floating on a field interaction. The electromagnetic force is keeping you separated from the chair by distances that on the atomic scale are still quite large. Your skin electrons and the chair's surface electrons never touch. They repel through the field, and you call that touching. Now I need to tell you something about the electrons themselves, because this is where people usually stop and where they should keep going. An electron is not a tiny marble with a charge painted on it. I want to be clear about this because the marble picture, while useful for some calculations, actively misleads you about what's going on. An electron is a quantum mechanical object, which means, among other things, that it doesn't have a position until you measure it. It has a wave function, a mathematical object, a solution to Schrödinger's equation that tells you the probability amplitude for finding the electron at any given location if you decide to look. The equation is I ps per t, h ps. That's psi, that's the electron. Not a particle, not a wave. A quantum state that has aspects of both and the full behavior of neither. When we say an electron is orbiting the nucleus, we mean the wave function has a particular shape around the nucleus, a probability distribution, and the electron's energy is quantized, meaning it can only take discrete values. The electron doesn't orbit like a planet. It exists in a stationary state, which sounds contradictory. If it's stationary, how is it moving? And it sounds contradictory because our intuitions were built for objects we can see, and an electron is not that kind of object. Here's the experiment you can run to see that this is real, not just philosophy. Fire electrons one at a time through two slits. You'd expect, if electrons were particles, to see two bands on the screen behind the slits, one for each slit, electrons piling up straight through. Instead, you get an interference pattern, bright and dark bands, exactly like what you'd get with waves. Even when you send them one at a time, each electron alone interferes with itself. It goes through both slits simultaneously. Not as a metaphor, not as a way of speaking, it literally goes through both slits, and its wave function interferes with itself, and it hits the screen according to that interference pattern. Now watch what happens if you try to catch it. If you put a detector at the slits to see which one the electron goes through, the interference pattern disappears. You see two bands. The act of measuring which slit the electron passed through forces the electron to be in one definite location, and once it's in one location, it can't interfere with itself going through the other location, because it didn't go through the other location. This is not a quirk. This is not an artifact of the detector disturbing the electron. This is quantum mechanics. Systems don't have definite properties until those properties are measured. The electron doesn't have a position. It has a probability distribution for position. And I'm telling you this because your hand is made of electrons and protons and neutrons, which are all quantum mechanical objects with wave functions without definite positions, existing as probability distributions until interaction forces definiteness. Your hand, strictly speaking, doesn't have a definite boundary. The electron wave functions of your outermost atoms extend out into space, decaying exponentially, but never quite reaching zero. The boundary of your hand is a matter of convention. We pick the radius at which the electron density has dropped to some small percentage and call that the edge. But quantum mechanically, your hand extends to infinity, very, very faintly. But it's there. Let me now tell you about the nuclei, because we haven't finished the story of what you're made of. The protons and neutrons in the nucleus are not fundamental either. By 1969, Jerome Friedman, Henry Kendall, and Richard Taylor at SLAC, the Stanford Linear Accelerator, were firing electrons at protons at extremely high energies, much higher than anything attempted before. If the proton were a solid ball, the electrons would scatter in a predictable way. Instead, the electrons scattered as if they were hitting hard, point-like objects inside the proton. 3 of them. The experimenters called these objects partons. We now call them quarks. The proton is made of 2 up quarks and 1 down quark. The neutron is 1 up quark and 2 down quarks. The quarks are held together by the strong nuclear force, which is carried by particles called gluons. And here the story gets strange in a new way. The force that holds quarks together doesn't weaken with distance. This is completely unlike electromagnetism or gravity, where the force falls off as the inverse square of distance. The strong force is approximately constant. As you pull quarks apart, you don't weaken the force, you store energy in the field between them. And you store enough energy that at some point it's energetically cheaper for the field to produce a new quark-antiquark pair than to stretch further. So you pull on a quark trying to isolate it, and instead of getting a free quark, you get a new meson, a quark-antiquark bound together. Free quarks don't exist in nature. Quarks only exist inside hadrons. This is called confinement, and we can describe it mathematically, and we don't fully understand why it happens at the level of the fundamental theory. So the nucleus of every atom in your body is made of quarks that have never been free, that cannot be free, bound together by a force we can calculate the effects of, but haven't fully explained from first principles. Your existence depends on a mechanism we don't completely understand. Now I want to bring this back to your hand, because we've gone fairly deep, and I want to make sure we've answered the question we started with. You are not made of matter in the way you think about matter, in the way that implies little solid things packed together. What you are, you're a configuration of quantum fields. The electron field permeates all of space. Where the electron field has high excitation, high energy density, we find what we call electrons. The quark fields permeate all of space. Where they're excited in particular ways, we have quarks. The Higgs field permeates all of space, and its interaction with particles is what gives particles like the electron and the quarks their mass. Before the Higgs mechanism, in the very early universe when the temperature was above about 10 circumflex 15 Kelvin, the electron had no mass. The electromagnetic force and the weak nuclear force were unified, one force, not two, and particles zipped around at or near the speed of light. As the universe cooled, the Higgs field settled into its current state, and mass appeared. Your mass, the thing that makes you feel heavy when you pick yourself up off a couch, is mostly not from the Higgs. This surprises people. The Higgs gives mass to fundamental particles. The electron gets 0.511 MeV from the Higgs. But the proton has a mass of 938 MeV, and the quarks inside it have masses of only about 2-5 MeV each. 3 quarks, each a few MeV, shouldn't add up to 938 MeV. They don't. The rest of the proton's mass, around 95% of it, comes from the energy of the gluon field binding the quarks together, =mc². The energy of the binding field has mass. Your mass is mostly the energy of fields. Let me make that concrete. Roughly 95% of your body mass is not from particles having mass. It's from the energy stored in the strong nuclear force fields inside every proton and neutron in your body. You are, in this very specific and calculable sense, mostly made of field energy. The boundary between matter and energy that we learn about in basic physics. Matter is the stuff, energy is what the stuff does, isn't a boundary at all. Mass is a form of energy. Energy has inertia. The distinction collapsed with special relativity in 1905, and it collapsed completely in our understanding of what nuclei actually are. There's one more piece I want to give you, because I think it completes the picture in a satisfying way. The pattern you see in the periodic table, the elements, their chemical properties, the way they combine, all of that comes from quantum mechanics applied to the electron configurations around nuclei, specifically Pauli's exclusion principle. No two electrons in the same atom can have the same quantum numbers, the same state. This means electrons fill up energy levels, and the outermost electrons, the ones that determine chemical behavior, depend on how many are left over after the inner levels are filled. That's why sodium and potassium, separated by a row in the periodic table, behave similarly. They both have one electron in their outermost shell. That's why neon and argon are both inert. Their outer shells are complete. The diversity of all chemistry, every reaction, every compound, every protein folding in your cells right now, every neurotransmitter enabling you to read this, is the consequence of one rule. Electrons can't share quantum states. That's it. The richness of chemistry is a consequence of quantum statistics. So here's what you actually are. You're a localized region of space where several quantum fields, electron field, quark fields, photon field, gluon field, Higgs field, are excited in a particular highly organized configuration. The boundary of this configuration is not sharp. The fields extend to infinity. The solidity you feel is electromagnetic field interaction, not particle collision. The mass you have is mostly field energy, not particle mass. The identity of the atoms in your body is governed by quantum mechanical rules that don't permit classical intuition. And this configuration, this specific excitation pattern in the fields, is not static. The atoms in your body are constantly exchanging. About 98% of the atoms in you were not in you a year ago. Different atoms, same configuration. You are not your matter. You're a pattern, a stable, self-replicating information processing pattern in the quantum fields. Now here's where I'm going to be honest with you about what we don't know, because this is important and people sometimes skip it. We can calculate with the standard model of particle physics to extraordinary precision. The magnetic moment of the electron, the way the electron wobbles in a magnetic field, has been calculated theoretically to 12 significant figures and measured experimentally to 12 significant figures, and they agree to 12 significant figures. That's the most precisely verified prediction in all of science. We know this stuff works. But we don't know why there are 3 generations of quarks. We don't know why the neutrino masses are so tiny. We don't know how to unite the standard model with gravity. Quantum field theory and general relativity are both extraordinarily successful. They don't contradict each other in any regime we can currently test, but they're mathematically incompatible in the extreme conditions near black hole singularities or the very early universe. We don't know what dark matter is, 27% of the universe's mass energy, interacting gravitationally, not through the electromagnetic force, not accounted for by any particle in the standard model. We don't know why the matter in the universe wasn't exactly balanced by antimatter after the Big Bang, a slight asymmetry, 1 part in 10 billion, left behind the matter that makes galaxies and planets and hands. The story of what you're made of has a precise, well-tested quantitative middle, the quantum field theory middle, with genuine open questions at the edges. Look at your hand again. Quantum fields all the way down, each extending through all of space, with you being a local high excitation region. The mass coming mostly from field energy, not particle mass. The solidity from electromagnetic repulsion, not contact. The boundary fuzzy. The configuration dynamic. The atoms themselves temporary tenants in a pattern that calls itself you. That's stranger than the solid stuff picture. It's also more true, and what I find remarkable about it, genuinely remarkable, not as a rhetorical flourish, is that the math describing it is beautiful. Maxwell's equations are beautiful. The Dirac equation for the electron, combining quantum mechanics and special relativity, is beautiful. The standard model Lagrangian is not simple, but it has a deep internal symmetry that's beautiful in the way that a good proof is beautiful, where you see it and you think, yes, that's how it had to be. The universe didn't have to be describable. It didn't have to follow mathematical patterns that fit in equations. And yet it does. And the patterns it follows are, when you look at them directly, quite beautiful. That's not mysticism, that's an observation. And I don't know what to make of it, but I find it genuinely wonderful that we can look at our own hands and ask the question seriously, and that the serious answer turns out to be this strange.